Now this diagram, which is a continuation of what we just finished up with on the last part, shows the formation of the hybrids from in the boron atom. And what you see on the left here is the boron atom and its electron configuration, with one electron in the 2p orbital and two in the 2s orbital. And what happens is you have two empty 2p's and one 2p that has an electron in it, and two of those three 2p orbitals hybridizes with the s to form three sp2 hybrids, and then each of those contains an electron which is half filled and accommodates an electron from each of three hydrogens, and that's how this forms. Now the central atom in each of these structures contains three regions of electron density, and therefore these would hybridize in the same way, 3 or sp2. As we know from the VSEPR, the regions of electron density contain all the electrons that point in a single direction. A lone pair or an unpaired electron, a single bond, or a double bond would each count as one region of electron density. Now if we have four, that is, you have each of the p orbitals, the x, the y, and the z, hybridize with a s, you end up with sp3, and you end up with four of them. And you can see here that these are each, two of the four are along the two axes, and then the other two are at 109.5 degree angles. And this gives you the tetrahedral arrangement. And here's an example of an atom that does that. Carbon starts out, as you can see, with the sp situation, or excuse me, the two electrons in the s and two electrons in the 2p. Each of the p orbitals, the px, the py, and the pz, hybridize with the s to form 4 sp3. And then each of these can bond with a sigma bond to form with hydrogen and form methane, CH4. The configuration of that will be a tetrahedral configuration with a hydrogen at each corner of the tetrahedron. Now when you start, this is a molecule of methane, and methane is a situation where you have two carbons, both of which have the 4 sp3 orbitals. One of those interacts with the other carbon to bind together, as shown on the right here, and then the hydrogens bond to the remaining 6 sp3 orbitals that are available. This ends up showing you 7 overlapping sigma bonds. Now things can get a little bit more complicated in situations where you have more than 4 orbits, and these are exceptions, but they do occur. And one hybridization is the sp3d hybridization. It's seen in this sulfur tetrafluoride and chlorine tetrafluoride, and you'll note that the middle chlorine or sulfur has 5 pairs or 10 electrons, so it violates the rule of octet, which is why I say it's a unusual situation. But in order to do that, it has to form 5 sp3d, and the extra one comes from the d. And then here is it shows the 5 regions again with phosphorus pentachloride. You have the 5 hybrid sp3d orbitals, and you have this unusual trigonal bipyramidal structure that occurs with that, with each of these pointing in various planes. As before, there are also small lobes pointing in the opposite direction. You remember those small lobes, but they are left out because it would be too confusing. And then lastly, you can have a situation where there's actually 12 in the central sulfur in this case, and it forms an octahedral structure. And as I said, this is fairly unusual. This is sp3d2 hybridization. So there are 6 sp3d2 hybrid orbitals, each of which points in a various direction and it ends up forming an octahedron. So the way to do these, in other words, the process that you undertake in order to do this, is you have to draw a Lewis structure of the molecule first. Then you determine the number of regions of electron density around the central atom using the VSEPR theory. Then you take that assigned, and using figure 8.21 in the book, it tells you what the hybridization is and what the geometry is. So here's a picture of that table in the book, and you can see that if you have 2 regions of electron density, then you have sp and it's linear. If you have 3 regions, it's sp2 hybrids and it's trigonal planar. If you have 4, and these 3 are by far the most common, you have sp3 and it's tetrahedral, and then the last 2 are self-explanatory and are also much less common. So this is ammonium sulfate, which, as it says here, is an ingredient in fertilizer, and also is how Timothy McVeigh made the bomb that blew up that building in Oklahoma. So first of all, what is the hybridization of the sulfur in SO4? Well, how do we go about doing this? Well, the first thing we do is we draw a Lewis structure. And I think we've actually drawn a Lewis structure for this molecule in class before, but I'm going to do it again just to remind you of what it looks like. And I'll draw it down here. So we have 6 here and 6 around each of these, so there's a total of 30. 6 times 5 plus 2 for the charge, so there's 32. Then you surround it with oxygens, and each of those represents a pair, so that's 8, leaving 24. And if you put 6 electrons around each one of these, you end up using all the electrons. So around this central sulfur, you have 4 regions of electron density, 1, 2, 3, 4, which is right here. If you look in the table, which was I showed here on the previous slide, 4 regions is tetrahedral, and so this hybridization is sp3, and it forms a tetrahedron. This next one, Se and SeF4, as it turns out, if you draw the Lewis structure here, you end up with something that looks like this. It's actually up on the board here. And you have an extra pair, so there are 5 regions. And if you look on the table, it's sp3d, which is the trigonal biplanar. Now let's look for a second at multiple bonds. So how does one describe the situation when there are multiple bonds? Well, the central carbon atom does hybridize, and it hybridizes to form instead of hybridizing to form 4 sp3s, each of which will bond singly, it has to hybridize so that there are 3 single bonds and then a leftover electron in the unhybridized p. So what you have, if you look on the right here, in a double bond situation is you have 3 sp2s, each of which has an electron ready to bond, and then you have a leftover p electron which is also ready to bond, and it's this p electron which forms the pi bond that we talked about before. So here is a molecule of ethene, which has a double bond between the carbons, And A shows the 5 sigma bonds with the hybridization, sp2 hybridization. And the sigma bond, or the pi bond, forms as a side-to-side overlap shown on the right here. Now what this wants to show you is how you would form carbon or acetylene or ethine, which is C2H2. And what happens here is you end up with sp hybrids and 2 unhybridized p orbitals with electrons in them. And so what you end up with is the sigma bonds again, and 2 double bonds. So the formula for acetylene, as is shown down here, is a triple bond, and the triple bond is these 2 red p's are overlapping in one pi orbital and 2 blue overlapping in another pi orbital. Actually, it's red and blue and red and blue, and that represents how you would form a triple bond. This shows the overall outline for this acetylene, and the 2 lobes of the pi bonds are positioned across from each other such that they can overlap as parallel bonding structures. Now, I'm going to show you a pretty complicated diagram, and I want you to look at the hybridization for each of the atoms in this. First, you have to draw a Lewis structure in order to do that. And this is what the Lewis structure for methionine looks like. You have the CH3 over on the left, and then an S, and you can see that you have 2 pairs of unbound electrons there, but that still represents 4 binding regions, or electron regions. And then you have the CCC, CH2, CH2, and then off of the 3rd carbon there on the right, you have a nitrogen, which binds to 2 hydrogens and has an open pair. And then lastly, you have this double bond O on this end. So you've drawn the Lewis structure, so what are the regions for each atom? So if you look at 4 of the carbon atoms, all of the carbon atoms except the one on the far right, each of those has, all of 4 of those have 4 binding regions. And the 1 carbon atom on the right has 3. The nitrogen has 4 binding regions as shown. The oxygen, each oxygen, one of them has 3 binding regions. That's the one on the upper one on the right. And the lower one on the right has 4 binding regions. And then the sulfur, as I said when I was talking about it before, it has 4 binding regions. So each one that has 4 binding regions, each carbon has 4 binding regions, will have an sp3 hybrid. The one with 3 binding regions has an sp2 hybrid with a pi bond. The nitrogen will have 4 binding regions, or sp3 hybrids. The oxygen, one oxygen will have sp2 and the other will have an sp3. And that's what's shown here. 4 of the carbons are sp3 hybrids. 1 carbon is sp2. The nitrogen is sp3. The oxygen that is double bonded is sp2. The oxygen that has a single bond is sp3. And the sulfur is sp3. And so that ends this lecture, and work on the homework. And if you have a problem, we will be having a help session on December the 1st.